All right, let's dive into a question that's right at the heart of writing good code. What actually makes one algorithm better than another? Today, we're going to pull back the curtain on how experts analyze code by looking at its best, worst, and average case performance.
So you've written some code. The first thing you're probably wondering is, how fast is it? Seems like a simple enough question, right? But as you're about to see, the answer's way more interesting than just a number on a stopwatch. Because really, the most honest and accurate answer is, it depends. It depends on the kind of data you throw at it. It depends on the specific situation. And today, we're going to get into exactly what it depends on. Okay, to really wrap our heads around this "it depends" problem, let's use a super simple and classic example, the linear search. If you've ever taken a programming class, you've seen this one. And there's a good reason for that. It's just so easy to understand. So here's the deal. You've got a list of stuff, and you're looking for one particular thing. All you do is start at the very beginning, look at the first item, and ask, is this it? If not, you just move on to the next one, and you keep doing that until you either find what you're looking for or you hit the end of the list. Couldn't be simpler. Now, that super simple process can actually play out in some really different ways. You see, depending on where our target item is hiding, we run into what we call the best, worst, and average cases. You can think of them as three different possible stories for how our search goes down. First, let's talk about the best case. I mean, this is the dream, right? It's when the item you're looking for is literally the first thing you check. Bam, one comparison and you're done. It is the absolute fastest our little search can ever hope to be. But on the total flip side, you've got the worst case. This is when your algorithm has to do the absolute maximum amount of work. It happens when your target is at the very, very end of the list. Or, even worse, it's not in the list at all. Either way, you're forced to look at every single item. And then, kind of in the middle, we have the average case. Now, this is often the most practical and realistic way to look at things. It answers the question, look, on a normal day with a normal search, what can I expect? It just assumes the item could be anywhere and it averages it all out. This little table sums it up perfectly. Best case, one and done. Just one comparison. Worst case, if your list has n items, you got to make n comparisons. And the average case, well, if you crunch the numbers, it ends up being about halfway through the list, or n+1/2 comparisons. See? Three totally different answers for how fast is it? So, we've got these three cases, but how do we describe them in a more formal, mathematical way? Well, this brings us to one of the single biggest points of confusion in all of computer science, the difference between cases and notations. I am almost certain you have heard this before. Someone says, oh yeah, that's easy. Big O is for the worst case, and big omega is for the best case. It sounds so neat and tidy, it feels like it should be right. But let me tell you, it is completely 100% wrong. It's a huge misunderstanding, and we're going to clear it up right here, right now. Seriously, getting this straight is a game changer for how you think about performance. Okay, here's the reality. Think of it this way. On one side, you have scenarios, our best, worst, and average cases. These are like weather conditions. Is it sunny, rainy, or a hurricane? On the other side, you have mathematical tools, big O, big omega, and big theta. These are like your measurement instruments, a thermometer, a barometer, a wind gauge. You can use any tool to measure any weather condition. They are totally separate concepts. You can describe the best case with big O if you want to. They are not tied together. So to really hammer this point home and see how deep this rabbit hole goes, let's take our new clear understanding and apply it to a more advanced data structure, the binary search tree, or BST. Now for a BST, the best case search is pretty obvious. You're looking for the item at the very top, the root. Just one check and you found it. The worst case? That's when you have to travel all the way down one of the branches to find an item at the very bottom, what we call a leaf node. But here's the twist. If I ask you about the performance of that worst case, what do you think the answer is? You guessed it, it depends. Because even within the worst case scenario of looking for a leaf, there's another variable we have to consider. And that variable is the actual shape of the tree itself. You see, not all binary search trees are created equal. Their structure can have a massive, massive impact on their performance. A binary search tree can look two very different ways. You might have a nice, short, bushy tree, which we call balanced, or you could have a tall, stringy, lopsided tree, which we call skewed. And the wild thing is, they are both technically valid binary search trees. The balanced tree is what we want. It's the ideal structure. Because its height is minimized, searches are incredibly fast. The skewed tree, on the other hand, is a performance nightmare. It's basically just a glorified linked list, and searching through it is just as slow as that simple linear search we started with. So this gives us two different kinds of worst case. First, you have the minimum worst case time. You can think of this as the best of the worst. This is when you're finding a leaf node, but you're doing it in a beautiful, perfectly balanced tree. The performance is proportional to log n, which is fantastic. It's incredibly efficient. And then you have the maximum worst case time. This is the worst of the worst. It's when you're stuck finding a leaf in that horrible, stringy, skewed tree. In this situation, your performance is proportional to n. All that clever tree structure gave you no benefit at all. Whew, okay, that was a pretty deep dive. So let's come back up for air and do a quick recap of the most important things to take away from all this. First, an algorithm's speed isn't just one number. It always depends. That's why we have to analyze the best, worst, and average cases to get the full picture. Second, and this is the one I really want you to remember, cases are scenarios and notations are math tools. They are two separate things. And finally, as we saw with our trees, even a single case, like the worst case, can have its own range of possible outcomes. And so I'll leave you with a question to think about. The next time you're designing a solution, which case are you going to build for? Are you going to optimize for the average day? Or are you going to make sure your code is bulletproof and can handle the absolute worst case scenario? The answer to that question says a lot about what you're trying to build. Thanks for watching.